All right, so last time we had started so-called Baire category theorem. Let me remind you what's the theorem. Uh, Theorem tells us the following: if X D is a complete metric space, and if a subset can be written as a union of closed subsets of X, then for E to have a non-empty interior, at least one of the ENs must have a non-empty interior. In other words, if all of these ENs have empty interior, then E cannot have a non-empty interior, so it has to have empty interior. Okay, and as an example, we discussed this example. Uh, X is the complete metric space R with absolute value metric, and we take the subset Q, and I can write, since Q is countable as a countable union of since Q is a countable set, I can write Q as a countable union of these one element subsets, each of which has empty interior. Therefore, we see that Q has empty interior. Of course, we knew this result already. I mean, it's not a surprise, but this is also a consequence of the Baire category theorem. All right, do you have any questions so far? Okay, today I'll prove this theorem, and if I have time, I'll start Arzoli Ascoli theorem. Now let's start this theorem. To prove the theorem, we need a lemma, and here is the lemma. Okay, let epsilon n be a sequence of real numbers. They're all positive, but the limit is 0 with limit epsilon n equals 0. If the closed ball with center xn and epsilon radius epsilon n contains, all right, or lies inside bxn minus 1 epsilon n minus 1 for all n larger than or equal to 2 and some sequence xn. So I have a sequence in x, so that when I draw epsilon n radius about each element of xn, I get a nested sequence of balls. If this is the case, then there is some x in x, so that the common intersection of these balls from 1 to infinity is the set which contains this single element. Okay, so in this case, you see I have a sequence, right? And so x1, x2 and so on. I have xn and it has, let's say, radius epsilon n, and inside this I have okay, xn plus 1, and the radius of this is something smaller, so that this closed ball, okay, lies inside the big one, epsilon n plus 1. Okay, in this case we see that the intersection of all these balls consists of a single point. Okay, all right. Let's see the proof of this lemma first. Well, we know that xn x is a complete metric space, and somehow we have a convergence of a sequence. So we need to show that this sequence is convergent, but since we are in a complete metric space, it is enough to show that the sequence is indeed Cauchy. Okay. All right. Now let m and be integers with m larger than n. Okay. Okay. Then by the assumption, right, if you take a ball with bigger index, then it is inside the uh, preceding one. So we have this ball bxn epsilon n contains bxn plus 1 epsilon n plus 1 epsilon n plus 1, and this contains the next one and up to the uh, mth one, right? Epsilon xm epsilon m. All right. Well, in particular, I have what? This xn, sorry, xm is in this ball, and thus the distance between xn and xm, or maybe I should try, is less than what? This is inside this ball, right? So the radius is less than epsilon n. I mean, the distance is less than the radius, which is epsilon n. Okay. Uh, well, we claim that, okay, let epsilon be given. Since limit epsilon n is 0, and they are all positive, there is some n 0, so that if n greater than n 0, then the distance between this real number and its limit is less than this epsilon. In other words, I have this. These are all positive, so I have this. Okay, but then you see, hence, thus, if m and n are both larger than n 0, then the distance between okay, the distance between xm and xn is less than epsilon n, but if if uh, n is larger than n0, then epsilon n is less than epsilon. So we have this. So what we see is this then. For any epsilon, there is some n0, so that if m and n are both larger than n0, then this distance is less than epsilon. This is precisely the definition of being a Cauchy sequence. Thus, xn is a Cauchy sequence in the complete metric space xt. Since xt is complete, xn is convergent. Say limit xn is equal to x for some x in the metric space. Okay. Well, you see, by definition, now let me write this sequence x1, x2, x3, xn, xn plus 1, xn plus 2, and okay, maybe this xm, and this is converging to x. What I know is this: x1 is in the first ball, and actually all of them, right? All of these are in b x1 epsilon 1, right? Because the ball around x2 already lies inside the ball around x1, and therefore all these elements lie in this closed ball. Maybe I should write like this. So all these lies inside this closed ball. And then starting from the second element, all of them lies inside b x2 epsilon 2, and similarly all the elements starting from x3 and on, they lie inside this ball. And this implies what? So this is 2 epsilon 2. I should be careful. Okay. Well, so this is a sequence. x1, x2, x3 is a sequence in this closed subset, and it is convergent, right? So since since b x1 epsilon 1 is closed, we see that the limit of this sequence, which lies inside this set, must lie inside this ball. And this sequence, starting from x2, x3, and going like x2, x3, this is a subsequence of this sequence. And this subsequence lies inside this closed set and it is convergent. Similarly, x is in B, x2 epsilon 2, and so on. So we have what? In particular, x is in all of them, right? The same argument applies to all of them for all n, so that x is in the intersection of all these balls. Well, we are almost done, right? We are almost done. But you see, we claim more than that. This intersection is non-empty. It contains a point, but we claim that it contains no other point. It contains only a single point. All right. So we have to show that this intersection contains no other element other than x. Well, if y is any other point lying in the set, then you see the distance between then y is in this ball, right? And uh, the distance between x n and y will be less than epsilon n, right? But this implies, so taking limit as n goes to infinity, we see that right, when we keep y fixed, this becomes a continuous function of the first variable, which is x. Since it is continuous, I can write this. This is just the limit of dx and y, because this thing is a continuous function of the first variable, right? This is the distance function from a point to a fixed point. And as you take limit, right, this is always, of course, non-zero, but the limit of epsilon n's is also 0. So in particular, dxy is 0, and thus we see that y equals x. So we are finished, right? Hence, this intersection from 1 to infinity of these balls consists of a single element, which is x. Okay. So this finishes the proof of the lemma. Okay. Do you have any questions so far? Okay. All right. So let's see. We proved this lemma. Okay. Now let's see why this helps us to prove the theorem, Baire category theorem. Okay. The proof of the theorem. Baire category theorem. All right. Remember, E is this, right? Union of E ends. And by assumption, what was the assumption? Let's see. These are closed subsets whose union is equal to X. E, sorry. And each En closed subset or all N. And let's assume that interior of E is not empty. Assume that X0 is in the interior of E. So this union has non-empty interior. What we want to show is then one of these ENs has non-empty interior. So we must show interior of En is not empty for some n. Maybe not all of them, but at least one of them should have non-empty interior. And to prove this, we will proceed again by proof technique with the proof technique in uh, proof by contradiction. Okay. Assume on the contrary that each En has empty interior. So we have to arrive at a contradiction. Okay, let's see how we will do this. Okay, okay. Now, since E since X0 is in the interior of E, there is some positive number epsilon 0 with the so that the ball X0 epsilon 0 lies inside E, right? Okay. Now, but E1 has empty interior. Now, since E1 has empty interior, this ball cannot lie inside E1 because if it were, then X0 would be an interior point of E1, but we assume that all ENs have empty interior, right? So, since this ball cannot lie inside E1, there is a point, right, in this ball which doesn't lie inside E1. Hence, thus, there is some X1 which lies where? Which lies in this ball but not in E1. So it lies in this set. Okay. However, you see, this is an open set and E1 is closed. So therefore, this is open. And since E1 is open, this is also open. So the intersection is open. Okay. Since this set is open, there is, and x1 is here, there is some epsilon 2 so that this ball b x1, sorry, not epsilon 2, epsilon 1, I should, we started with epsilon 0, epsilon 1, so that this ball, right, this is inside this open set, so this ball should lie inside bx0 epsilon 0 intersection x minus e1. Okay. Well, maybe I should let this epsilon 1 prime, because I will be more careful to choose epsilon 1. Now let epsilon 1 to be this number, minimum of this number and 1. Then I have this. Since epsilon 1 is already less than this, this ball, not this is not open ball, this is closed ball. Yeah, and sorry, epsilon 1 prime over 2, let me choose. Yeah. Then this ball, you see, epsilon 1 is less than epsilon 1 prime over 2, and this is strictly less than epsilon 1 prime. Thus, the ball with center x1 and radius epsilon 1 lies inside this open ball, and that lies inside this ball. Okay. And then we do what? Okay. Well, since similarly, since E2 has empty interior, this ball so I play the same game. Okay, this ball cannot lie inside x minus, so it cannot lie inside E2. Okay, E2, because if it were, then x1 would be an interior point of E2. So hence there is some x2 which lies inside this ball and outside E2, playing the same game. Okay, playing the same game. So similarly, we find epsilon 2. This time epsilon 2, so there we will first choose epsilon 2 prime and so on. This epsilon 2, so that epsilon 2 is less than, it will be less than 1 over 2. Okay, so I'll divide this, instead of 1, I'll take 1 over 2. And I will have this ball epsilon 2 x2 will lie inside x1 epsilon 1, and this lies inside. Okay, yeah, maybe I should be more careful. First we have this lies inside x minus e2, and then b x1 epsilon 1, and then okay, so I have this lying inside this closed ball, and this closed ball lies inside this closed ball. Okay, so this way, by induction, we construct a sequence of balls b x n epsilon n, so that epsilon n is non-negative. I mean they are positive but less than or equal to 1 over n. Each time I choose my epsilon to be less than 1 over n. Epsilon 1 is less than 1, epsilon 2 is less than 1 over 2, and so on. I just keep doing this so that we have this, and b xn epsilon n contains b xn plus 1 epsilon n plus 1. Well, this is precisely the assumption of the lemma. Thus, by the lemma, the intersection of these balls okay, is just x, for where x is nothing but the limit of xn. So the lemma says that this sequence is convergent. Moreover, the intersection of these balls is just x. Okay, but this will lead us a contradiction real quick. Why is that? Since this x is inside this ball, and by the choice this lies inside this, right? Remember, uh, B x1 epsilon 1 is chosen so that this lies inside this set, right? B x2 epsilon 2 is chosen so that it lies inside this set, sorry, this set, and B xn epsilon n is chosen like this. Okay, for all n, x is not in En. So you see, x is in this ball and it's not inside En for all n, and thus x is not so x is not in En for all n. Thus, therefore, this x cannot be inside in the union of these Ens because it is not inside any of them. Therefore, it cannot be in the union. However, on the other hand, x is in, of course, this ball b1 bx1 epsilon 1, right? And this lies inside by the construction x0 epsilon 0, and this lies inside this ball. Yeah, here I have open. So we have this, right? This union is equal to E. X is not in this union, but here X is in that union, which is a contradiction. Okay, it's a contradiction. Okay, what is the reason of the contradiction? We arrived at this contradiction because we assume that, on the contrary, each En has empty interior, right? So that assumption is false. Therefore, at least one En must have non-empty interior. Okay, and this finishes the proof. Any questions so far? This proof, is different than what we have done so far. Okay, it contains some ingenious ideas. As I said, several times, I don't expect you to memorize the details of the proofs. Uh, you just need to know that what the theorem tells us, okay, and should be able to exhibit some examples related to this theorem. Now I will give you, for example, one example. Uh, Now R2, right, with the Euclidean metric D2 is a complete metric space. Metric space. Any line, line L in R2 has empty interior, right? Has empty interior and is a subset is closed. Okay. Why is that? Well, you see, whenever you take a line, this is a closed set. Why is that? Because if you pick up a point outside this line, then you can draw a ball, epsilon ball around this, right? Some ball or radius with r, so that this ball doesn't touch the line L. And if you choose, so this shows that L is closed. And if you choose a point here on the line, then no ball around this point lies inside L. And this shows that L has empty interior. So we have this uh, uh, any L is a closed subset and it has empty interior. Of course, R2 is a complete metric space. Therefore, by the theorem, we see the following. So, if let's say E is a union of some lines from countably many lines, then uh, interior of E must be empty, okay? Because I have a countable union of closed sets where each of them has empty interior. It doesn't matter how many of them, provided that their number is countable, so L1, L2, L3, infinitely many of them, then the union must have empty interior. Right? This is not actually, uh, easy to see, right? I mean, I have infinitely many lines, okay? And no matter how you draw them, the union has always empty interior, okay? This is what the theorem tells us. Okay. Do you have any question so far? Okay. The next theorem will be the next topic we will consider is so-called Arzoli-Ascoli theorem, or maybe I should give you one more example, but maybe in the second hour. Uh, all right. Uh, yeah. Okay, so we claim the following. The set of irrational numbers, let's say P, which is R minus Q, uh, is not contained, is not contained in the union of uh, countably many closed subsets with empty interiors. So note that the set of rational numbers, on the other hand, can be written like this, right? This is a countable set, R1, R2, R3, countable. Therefore, I can write Q as the union of this one-point sets, where each of these are closed with empty interior. But we claim that you cannot do this to P. You cannot write the set of irrational numbers as the union of countably many closed subsets with empty interiors. Okay, you can do this to Q, but not to irrational numbers. Let's prove this in the second hour. Let me give a break. After the break, let's consider this example.